G'day, welcome to another High Performer Building Pulse. Thanks for joining us. Thanks for coming along for this journey. Today we are joined by Tim from Concrete New Zealand, and this episode has been sponsored by Stackcell and Amcrete, obviously two innovations that are critical to using concrete. But also, before I get in too much trouble, make sure you like and subscribe, and ideally just pass the word on and spread the word about all this amazing content, and always open for feedback and ideas, so let us know. That's enough for that. Tim, tell us a little bit about yourself, about Concrete NZ. Just give a little snapshot of your journey and how you've ended up where you've ended up.
Yeah, let me start by thanking you for having me. It's a great opportunity to sit here in your studio and spend the time with you. So just briefly, obviously you can hear that I'm from Germany in my accent. Spent 20 years in the global iron and steel industry, and the last 3 years there as global head of green steel.
Okay.
So looking into decarbonizing large-scale industrial assets
globally.
globally. So that's where I come from. I'm a mechanical engineer by background.
Okay.
And so from there, I got over to here as Concrete New Zealand's sustainability and policy director. So broadening the scope a bit in terms of sustainability, looking into all kinds of things like air emissions and spatial requirements and water circularity, material circularity. So really kind of dealing with the whole aspect of the supply chain.
Yeah.
Concrete New Zealand is the one industry body in New Zealand.
Okay.
So we have about 500 members, 90 of which are producer members. So they come from a very broad variety of sectors.
So 90. So we're talking all sorts of suppliers, obviously not just the concrete.
Yes.
That we know of.
Yeah, we have them in various sector groups. So 4 of the members are the main cement suppliers into New Zealand. That's our cement sector group.
Yeah.
Then we have a ready-mix concrete sector group.
Yeah.
That's about 40 to 50 individual concrete producers across the country, batching concrete on nearly 200 plants every year. Then we have precast producers, factory producers. We do have masonry producers.
Okay.
And eventually we just set up a reinforcing processors sector group for the people delivering the steel into the concrete market.
Interesting. I mean, the thing with concrete, obviously, it's a critical element in so many buildings. We're never going to get away with it from it, nor do we really want to, because it does a lot of things so well. But it does have a really kind of big bad name around it, right? And
it's a perception, at least.
Yeah, that's what I'm saying. So the perception is like, gosh, this stuff's terrible. And as far as a carbon journey, you've obviously done a whole lot of stuff there. But on one hand, it's got a lot of work to do. But unlike other industries, I mean, it's kind of starting behind the start line in some ways, but it's got a lot of work it can do by the sound of things. So I'm keen to get into a bit of that with you. Do you want to, before we go deep dive into that whole carbon and sustainability story, is there more we should be talking about than with concrete than just jumping straight to the hot bit?
Yeah, I think there's a couple of things. Obviously, we acknowledge the carbon footprint, and the industry has published and working towards net zero carbon footprint. So published a roadmap in 2023. And we identified 7 levers across the concrete industry, which we can pull to varying degrees influence our overall carbon footprint. And work towards the roadmap is progressing quite fast. So we see, for example, the cement production side already drawing down emissions by implementing new technologies, further and further reducing our reliance on coal energy input at the front end of the value chain. But then, as you say, all the stakeholders in the concrete value chain have some influence, and that's a good thing about concrete, I would say, have some influence over the composition and the carbon footprint of the material eventually. So that's what we are looking at currently, is kind of getting everyone on board, the specifiers, the placers, the contractors, the politicians, so everyone kind of understanding what is involved in drawing down low carbon or drawing down the emissions. And producing low carbon concrete. But as you say, right, that's just kind of the carbon bit.
Yeah. There must be other innovations that are spin-offs of that process as well, hey?
Yes, innovations, but also, I guess, a lot of misunderstandings that are currently tied to concrete, making people think that concrete has a greater environmental footprint than it actually kind of has. And I think a couple of things, just to mention a few examples. I hear people regularly saying that concrete is an energy-intense material, which is not true, because I think we have to be very, very judicious with the terms here.
Yes.
Concrete uses cement as a binder, as a glue, and that makes up about 10% of the final concrete. 10, 12%, depending on the strength grade and composition.
Is that the stinger, though, in the whole calculation? That's the bit that costs you for the carbon?
Yes, that's 80% of our carbon footprint. Sometimes
Right.
85% of our footprint is just the cement.
Right.
That cement has another product that goes into it, which is clinker. And the clinker bit is where all the energy intensity and the emissions intensity sits.
Yeah, now you mentioned this before we started filming. I'd never heard of clinker. Tell everyone what clinker is.
Now it's essentially just you chuck in limestone, ground limestone,
right,
with sand and a couple of other elements into a clinker kiln, and it gets baked by 1500 degrees.
Right.
And it partly liquefies and reshapes into these little bubbly whatever balls that roll off the mill.
Oh, wow.
And these then are being put into a cement grinding mill together with further limestone and some gypsum, and is then blended and ground into the cement that everyone knows as a precursor to the concrete.
Yeah, gosh. I'm assuming all of that's done because it makes it an incredible bonding agent.
Yes.
Otherwise you wouldn't bother, right?
Yeah, we need to make the limestone reactive and to hydrate when we put in water into the mix.
Yes.
So that's what the whole clinker production is about. The thing is, due to the dilution of the cement in the concrete, the final energy intensity of a cubic meter of concrete is about 1/10 of the energy intensity of a cubic meter of timber.
Yeah.
And even just to put some perspective to it, even if you compare a ton of cement with a ton of wood product, which is obviously a ridiculous comparison, but if you did it, the timber product would have double the energy intensity than the ton of cement.
So hang on, explain that for me, because it sounds like you're twisting the numbers to make it sound.
I'm just trying to give some perspective to things, because people say cement is energy intensive. And
cement
obviously, cement is.
And we've established that cement is 85% of the carbon load of the concrete. My question for you, though, are you switching to weights instead of volume because it sounds better?
In that final cement timber comparison, yes. That's not entirely...
Now, I'm not going to chastise you completely for that, because concrete is serving a purpose that needs mass, right? So you can't just say, oh, well, we'll just switch back to cubic meters, because not necessarily a cubic meter of timber doesn't necessarily do what a cubic meter of concrete does.
Now, that is a comparison that is much more legit, because if you compare typical comparative life cycle assessments and you compare different building typologies, usually you end up with a similar amount of timber as the concrete that you displaced. There is volume-wise. There is potential to reduce the timber volume in higher buildings, especially because timber weighs less and thus requires less volume to support itself. But in a warehouse or like a low-rise, mid-rise building, typically those advantages are not that pronounced, and you need the volume, especially in seismic areas, and also to kind of balance the structural performance of the building overall. You need to chuck in a lot of steel as well. And there's a sliding scale between the more pure you want your timber to be, obviously the more volume you need, and that escalates quite quickly. So
interesting. I mean, we're seeing a lot of hybrid buildings anyway. But I mean, the other thing is timber's going to serve a role.
Yes.
it's never going to be a complete switch. It's never going to do everything.
Now,
It's
anything
going to maybe have a dent, but not, you know,
anything in
not
ground
that big.
contact is the exclusive realm, more or less, of concrete.
The exclusive what?
The exclusive realm, the exclusive sphere of concrete, where
Right.
when you
realm,
want to
yeah.
build durable and like resilient
Yes.
in the environment, and you
Yeah.
have ground contact, then typically you use concrete.
Yeah, right.
And that's like where the vast majority of concrete goes to.
Yeah. All right. So lay out the roadmap for me. What are
Mhm.
the kind of the key milestones that are on the roadmap?
Yeah, milestones. I guess we have the first target is 2030,
Yeah.
where we intend to reduce our absolute embodied emissions against the 2020 baseline by 44%.
Okay.
And
And
the
what are
final
the
target.
steps to getting there?
Yeah, walking quickly through the levers. The first lever, obviously, is the clinker production,
Right.
and now the one clinker producing facility in New Zealand is up in Whangarei in
Yes.
Portland. They are already implementing world-leading amounts of alternative fuels
Right.
to replace their coal input.
Yep.
They've just recently commissioned a so-called front-firing technology that allows them now to replace about 70% of their coal by
Right.
these alternative fuels, and they are able to reach up to 85% in the short term
Right.
with that technology already installed.
Yeah. Right.
So they've started investing in that in the early 2000s,
Yes.
and have been at it for 20 years now, and
Yeah.
successively implemented more and better technologies, reaching a kind of performance that's comparable to the best plants in Europe.
Brilliant. And how much of a difference is that going to have on that?
Yes.
Is that the biggest lever to pull?
Not entirely. So the this lever is or the energy emissions in the cement are about a third of the embodied emissions of cement. 2/3 are from the chemical conversion of limestone into clinker.
Right.
So the limestone is CaCO3, and what comes out is CaO. So
Right.
release CO2 is
Right.
basically a part of the limestone.
Right.
And that's 2/3 of the production
Yeah, that's
emissions,
gonna.
what we call unavoidable process emissions. So the second lever is about that. It's basically about replacing part of the cementitious function of cement with alternative materials, which we
Right.
call supplementary cementitious materials.
Yep.
And pozzolana and
Yep.
novel cements. And that is our longest short-term lever right now, just because New Zealand doesn't have a long history in using SCMs.
Yes.
We've been at about 1.5% overall of all cementitious input in 2020, where the roadmap baseline sits. And we've now, over the past 6 years, we've got that to 6.5%, or actually over the past 5 years, because our last sustainability report has been published last year. So we see steep increase in uptake of SCMs. We have all the import.
When you say increase in uptake, is that the producers, or are they managing to drive the demand at the other end as well?
Yeah, that's the thing, right? The whole value
Yeah.
chain plays a role here.
Yeah.
Obviously, there is a concentrated uptake in the urban centers,
Yes.
Auckland, Christchurch, Wellington.
Because some of these alternatives, like my understanding of pozzolans is you've got a shorter curing time with it, so then you're a little bit more limited, and
Yeah,
it takes too long to get there.
yes.
Then the guys go and bloody add water to get it a bit more workable, and now you've lost your strength.
Yeah, that's the thing, right? I mean, that's in places like Germany, where I come from, we started using.
Not fair. You just can't keep comparing us to
No,
Europe.
or easily. I mean, I use some data to back that up. I mean, the annual mean temperatures in Germany are about the same as in New Zealand South Island.
Right.
But much, much worse than North Island
Okay.
annual mean temperatures. So, like the placing conditions, the climate conditions are great, actually. And we started using slag cement in the 1870s.
Wow.
So 150 years now.
like what sort of proportions of it?
It was like a single plant starting to
Yes.
do it, and they've been ridiculed in Germany
Yeah.
for decades for doing it. But in the
Why
early,
did they do it? Because there wouldn't have been a carbon driver
it's a
back
cost thing, right? I mean,
Right,
it's
okay.
helping them optimize the cost profile.
Yeah.
Just mix in some slag.
Yeah.
And over time, it took them like 30, 40 years to prove the actual performance
Yeah.
comparability of slag cement versus normal cement. And then it got standardized in the early 20th century, 1920, 1930. It got slowly into the standards.
Yeah.
And so it's a very long history. And the average clinker replacement level in Germany is about 30%.
Okay.
Sitting against our now we do have some mineral additions, as I said, in the cement. So when you convert clinker to cement, you grind some limestone, you grind some gypsum into the final material. So I would say on average we are probably sitting at 80, 85, 87% of clinker ratio.
Right.
That's the value that we are typically reporting.
Is all our limestone sourced locally?
Yes.
And gypsum was a form of limestone as well, wasn't it? Or
yeah, it's. Don't ask me about the details.
Sorry, concrete New Zealand.
No, I mean we are representing the cement industry just the same. But I could tell you a lot about steelmaking technologies. That's just because where I come from. But yeah, it's
So the other thing I'm interested in, say 40% of cement is imported. I heard that somewhere else earlier as well. Do we have enough volume to supply the whole market, and it's actually just market forces at play, not wanting to be secured, and we don't want to be locked into one, supplier and have them hold it over us? Or is there actually not enough, and we're always going to be importing regardless?
I guess what's not enough is the manufacturing capacity of that single plant in New Zealand. So they couldn't possibly supply all the cement currently that is required. So we use about
materials not a problem.
Yes, the raw material is not a problem, not at all. I mean, talking about raw materials and coming back to that environmental argument a bit, maybe. Obviously, you hear people say, okay, we're overusing sand globally, right? We are extracting more sand globally than is actually being replenished.
Right.
And when we talk about replenishing, then it's obviously marine processes, but there's also like a river sediment outflow into the oceans. And I kind of looked into the MFE publications on the quantities that we are talking about for New Zealand. And actually, if you run the numbers, we have more sand regenerating from our rivers than we use in New Zealand.
Yeah.
So that's the slightly more appropriate comparison for the New Zealand context. On the other hand, all that sand sits in the wrong places. So it's not like in Auckland where we use the majority
to move
of
stuff
concrete.
around New Zealand too.
So the further you zoom in, the more that becomes a problem again. But but still, the footprint of our extracting, like the quarry industry, essentially, is minuscule compared, on a cubic meter of concrete. We use about, let's say, half a square meter, a bit more than half a square meter of spatial requirement for a cubic meter of concrete. Compare that to 70 times as much, 70, for growing a structural timber product.
But then their argument's going to be theirs is replaceable. We can keep growing more once yours is out. One day you might break it down, put it back in the hole. So in some ways it's just moving the deck chairs.
Yes, indeed. But obviously what's happening is you're locking that land for indigenous biodiverse plantation, right? You have these monocultures sitting there, and they do change the soil as well over time, right? It's not like just the extractives are doing something to the ground. And when it comes to the quarry sector, typically the footprint is overcompensated for nature and nature impacts. So even the typical resource consents requires a quarry operator to compensate for the impact on the environment, and that can be as much as 4 or 8 times the spatial area of that quarry.
Right.
So and even when the quarry is gone, about, let's say, a third of our quarrying happens in riverbed areas, alluvial areas. So these are turned into basically compensation areas for river flooding, and also given that our kind of civilized society has started settling close to these rivers,
Yeah.
which traditionally, if you let them alone, they would just accumulate sediment and then change flow
Yes.
when things change. We are more reliant on that management of the river flow, and the quarry is actually taking out some of that sediment and helping the river flow again. And
Yeah.
with those areas that are left after the quarry is gone, they help basically like a battery, like a water battery,
Yeah.
to prevent flooding in areas. So it's all a bit. I mean, it's a
Okay.
diverse picture, I guess. It's
Yeah,
all
I
it's all
hear
about
you.
the details in the end.
The challenge you've got is it sounds like spinning. You know, and I'm just being upfront because
Yeah.
because it's better to just have it up front. And I'm not against it. I part of my problem, I think, is that we've ended up in this position where it's concrete v timber, and I don't think that's helpful for the industry. I think that we need to figure out how to get these two things working cohesively together. Because if you sit there with engineers and architects, they're just trying to build a building, right? There is a whole bigger picture at play. I get that. There's billions of dollars around the world funding low carbon projects that in some ways, as a concrete industry, you must be feeling is pressure against you. And so tell me about the other levers.
Yes. Okay. So we've been talking about the clinker and the supplementary cementitious materials.
Yeah.
They together are about 40% of our journey. So that's the
right.
biggest chunk, obviously, as we discussed, 80% of emissions in cement. And if we stay with the cement for a bit, the cement still serves an integral function in getting the hydration process started.
Yeah.
So it works in combination, in tandem with the SCMs. And while there are projects using cement-free mixes in some very innovative projects, like, for example, the London Power Tunnel project, they've been placing a cement-free concrete already. So basically, it's geopolymers with activators, but it's very, very technical.
Yeah.
For the vast majority of mixes, we'd still require cement as a reaction starter.
Yeah.
So the final emissions, the process emissions that remain, then we talk about carbon capture and sequestration, or carbon capture and utilization, and that's essentially where you plug in a carbon capture facility at the stack in Golden Bay,
Right.
and you filter out the CO2 in the off gas,
Yeah.
capture that CO2, and then you can do something with it. So either you use it to produce alternative fuels, for example, so you can combine it with hydrogen and produce hydrofuels that are essentially industrial off-gas CO2, and then hydrogen turned into something chemical inputs, fuels.
Which sounds wonderful, but I suspect that's a very expensive
the big
bit of kit.
I would say, from my point of view, and having worked in the steel industry, the big catch is the hydrogen, because hydrogen is a scarce fuel, and it's to have that hydrogen also green, so produced from electrolyzers, requires a lot of energy. So when you're sitting in like an electrically abundant, low cost energy situation, then obviously you can start thinking about that. But that's not exactly where we are in New Zealand right now. So the other thing is, obviously, you can use CO2 as in greenhouses. You can use it in the food industry for beverages and stuff, beer, Coca-Cola, everything. That's the utilization side of CO2. And there's more happening, right? There's a whole body of research around how can we use that CO2. The other thing is taking that CO2 and injecting it into depleted gas fields underground.
Right.
And I mean, those gas fields have held on to their methane for millions of years. So obviously you need to do some monitoring, and that's happening. For example, in Norway, there's a couple of big projects that have been operating for decades now.
So how does that work? They pump it underground?
It's basically the reverse process. So all the technology we have from the oil and gas industry,
right,
and also the capturing bits, typically like natural gas, as they call it, when you pump it out of the ground, very often it has too much CO2 in it.
Right.
So what they do, they capture the CO2. They use already the exact same technologies that we would need to capture the CO2 at the stack in Golden Bay. And they are becoming more efficient too. Just last year, the Nobel Prize in Chemistry went to a couple of researchers having invented a new form of carbon capture technology, metal organic frameworks. So that it decreases the energy consumption of the capturing process greatly. So yeah, it's basically just a reverse process, right? You put it underground, and then obviously, since you have drilled holes into the reservoir to get at the methane, you have to monitor. You have to make sure that the CO2 isn't escaping. Right. Again, which can be done, right? There's a certain kind of due diligence to be set up. Yeah. And so that's something obviously that comes more to the end of the journey of the roadmap. And if we get there, and I mean, obviously we get there. Sorry, when we get there, to use the better term, obviously there will be the question: okay, how much of it do we still need? Yeah. So what we are currently counting for is like the entire process emissions of the facility at Golden Bay, which is roughly 500,000 tons, which is equivalent to the first cement industry projects currently in operation in Europe. Yep. So we have those scale already operating elsewhere. And then the interesting thing is, since we have already replaced all the coal and we are using large amounts of waste timber and waste tires, and even waste tires contain a biogenic rubber component. So if you count all these biogenic kind of components together, you're basically sequestering biogenic CO2. Right. Part of the CO2 you're sequestering is biogenic.
You better explain to us what biogenic CO2 is.
Yeah, biogenic is, I guess that's a renewable component, right? It's basically you're capturing something out of the atmosphere by growing trees. That's a good thing about timber products in the end. So that is what biogenic basically means, is that it's coming in the growth process of the plants. Okay. And so sequestering atmospheric CO2, which is, by the way, the same thing that concrete does. That's another lever in the roadmap.
Yeah, over time, right?
Over time.
Continue to...
It basically reverses the chemical reaction that we did in the clinker production stage. Yes. By turning the hydrated cement back into a limestone-like formula, CaCO3 again, because that's the natural state. That's where it wants to be.
Yeah, right. But it must be a very slow process. Or
it is. Yes.
As it does that, does it weaken over time, or?
No, the thing is, it doesn't weaken. It actually hardens over time in that process. The thing is, we engineered against it because that changes the pH value in the concrete, and eventually the reinforcing steel in the concrete is so that's kind of the natural end of life of a concrete when the steel starts to corrode because the pH value isn't protecting it anymore. So the thing is, you can design again against that, right? You can increase the cover, for example, over the reinforcing steel to extend the time it takes for that that change to reach the reinforcing.
Yeah, right.
And
it's so flipping complicated, isn't it?
Yeah.
So many different parts.
And as you say, the process is very slow, especially during the life of the concrete, during the life of the building. Yeah. Because relatively little of the surface is exposed to the atmosphere. I mean, if you have like an exposed slab, obviously, that's the ideal condition for CO2 uptake. Yeah. When you look at it from a sustainability perspective. But if you have it underground, or let's say you have it, we have it underwater, even. It doesn't interact with that carbon atmosphere.
What about within the building, though? Is it capturing?
Yeah, if you put paint on it, it's already
covered.
It's covered. Yeah, or carpet, for example. So
so only where it's you can see the stuff, is it? Yeah,
exactly.
Which is the same for any material.
More or less, yes, exactly. And then when you break it down at the end of life, it multiplies in terms of surface area.
Right.
And that's when carbonation happens much faster.
Right.
So even in the 3 months, when it you break it down, you have the rubble on some kind of intermediate storage. It takes up about half the CO2 it took up over the entire lifetime of the building. So it's a very, from then on, a relatively fast process.
Yep.
And it continues that process even if you use the concrete for road fill or for like other purpose where you leave it in the environment.
Yep.
It still continues to carbonate over hundreds of years. Then obviously.
And so a lot of these things you're talking really about the local supply, because that's all you can have an impact on, right?
No,
But in terms of if we're talking clinker and cement and
yes,
not the stuff we've just been talking about, but yeah, like that's the how much can you do in terms of importing? That's
but let's define local supply again. I mean, you said 40% of cement is imported. That's right. About that much. That's about 6% or 5% of the entire raw material input into the concrete.
Yeah.
So more than 90% of our raw material is locally sourced, just because it doesn't make sense to ship around limestone, right? No. It's available, it's abundant. And obviously through procurement you have alternatives to importing higher carbon cement, and obviously it's something that everyone is currently looking into how to optimize their raw material.
Certainly as we get into alternative to cement, I understand, then we really get limited in New Zealand. You have to import, is that right?
When it comes to industrial byproducts, mostly, we do have the Huntly Power Station producing some fly ash, which has been used traditionally. So that was basically the 1.5% of SCMs that we've been using.
Yeah.
Pushing the.
We only get fly ash when they're burning coal, or do we get it when they're burning gas as well?
No coal. It's coal exclusively.
Yeah. Yes. So we're kind of pushing the story up the chain a bit there as well, right?
And we have landfilled fly ash, so that's a trend that you see, for example, in places like South Australia and Europe as well.
Yeah.
Where coal power plants are being decommissioned.
Yes.
People are now looking for reclaiming that landfilled fly ash, and we do have landfilled fly ash in New Zealand, quite a lot, in fact. So we can dig at that eventually.
Yeah.
If like all the material testing and things turn out to be, yes, this is reactive material that we might be using. So that's basically the other major SCM that we use is slag, which is mostly blast furnace slag, because a blast furnace is a reducing furnace. So what comes out is relatively pure in terms of what we require for the industry. And that's about half of our SCMs today. Okay. The other half is the fly ash now. So slag is catching up very fast with the fly ash dominance previously.
Yeah.
The other things that we are developing locally is we have clay, kaolin clay, for example, that we can turn into calcined clay, which works as a pozzolanic cementitious material. And we have pumice, we have perlite, we have a lot of the kind of naturally occurring materials here, especially as a volcanic active country.
Yes.
So the Romans used pumice, for example.
Right.
And we have pumice here. So it's a relatively light material, so it needs to be processed, needs to be dried. And obviously the testing is still to be done, but we have used pumice in the past. And it's just more like a rediscovery and also like an upscaling that's currently happening, where the industry looks into business cases and how to make that happen at scale. So that's kind of the medium to long-term transition that we will see developing towards more local materials. Also, maybe a thing that is happening in Europe right now is limestone, just the kind of the plain limestone. If you grind it very, very, very fine, ultra fine limestone essentially, and you use it in your concrete mix, it serves as an accelerator and increases the efficiency of the cement reaction. Okay. So you can reduce your cement, your cementitious input, when you offer the cement more surface area, more fine particles to react to. Yeah, right. So it's not like essentially like acting like an SCM, but it is acting as an agent to reduce the cement input.
Interesting. Is it ever possible to have electric arc furnaces for do they get hot enough?
Now the thing is, let's start with the steel side maybe quickly. Okay. Our unique steelmaking process, the legacy process that we have in Glenbrook, in the New Zealand steel plant, has a very peculiar emissions profile because we use iron sands that we convert with a coal-based rotary kiln, and then it goes into a smelter furnace. That is comparatively high.
Right.
When it comes to steel products, typically also the high-grade steel products are usually flat steel, so like sheets and automotive exposed grades, and they usually need higher shares of virgin material like iron ore, iron sands.
Rather than trying to extract the ore out of the sand, right?
Yes.
Yeah.
While rebar, the stuff that we use in concrete, typically comes out at the lower end of that scale. So it's entirely possible to produce rebar from 100% scrap feed.
Right.
And that's what like the rest of the world did for decades, for a long time. And that has a hugely better emissions profile. So it's like an eighth of the embodied emissions in the rebar. And that's what we are now seeing happening here in New Zealand with the new electric arc furnace. It will be able to produce 100% scrap for a couple of heats, but the default process will be 50% of the legacy virgin product feed and 50% scrap, blending to about less than half the emissions of the current steel. It has to be said though that steel is not entirely new. We had content in there. We did have access to recycled steel via imports. There have been a couple of companies that brought in recycled steel, like Nauria, for example, from places like Singapore, which had already greatly reduced carbon footprints. And it's just now that we are kind of commoditizing that level of embodied emissions.
While we're on rebar, I've seen alternatives. I've seen fiberglass. I've seen one that we get all sorts of products dropped around here that are interesting. And one I think was like made out of basalt or something like that. Mm-hmm. Why aren't those things taking off? Is it cost? If it is cost, do they just need scale, or are there other issues there? What do you think? I mean, you must be seeing it on a more global perspective, right? We've got all sorts of local challenges, but why don't they take off globally?
I guess it's all of these things, right? It's cost, it's standards. Standards allow for a certain mix of, let's say, steel fiber or FRP fiber in the concrete. But that requires additional testing, that requires the specifier, again, to work with that material, to trust in that material. The engineer, the structural engineer, is basically to believe in that material. Obviously, that those materials have huge potential for once to reduce the risk of corrosion. I mean, if you use FRP rebar, obviously there's no corrosion happening ever. No. But also if you use like fibers, for example, like individual steel fibers, also like these little chunks that you chuck into the product. A large amount of working hours on site are spent tying the rebar together. So using fibers, a lot of those hours can be replaced by just chucking in some fibers. And but it's not everything, obviously.
Yeah, well, from memory, we used to do a lot of work with Allied, and it was a brilliant product. But from memory, you used to end up with a big thick slab without kind of footings, or there must have been footings in load-bearing areas, but you didn't have the ribbing or the waffle, so you ended up using more concrete, but the overall process was a lot faster, and it was still quite cost-effective. But it obviously doesn't help us on a carbon journey if we end up using more concrete.
I guess it comes down to the specific engineered solution, right? How much steel shares there, how much embodied carbon is in the fiber. The circularity would probably also be affected if you use a lot of fiber in your steel, like little individual fibers, because recyclability is impaired to some degree.
Yeah.
And that's something also, again, it's this kind of thing in Europe where they start to recover the cement paste from crushed concrete.
Okay.
So you basically you bake the crushed concrete because when you come across a certain temperature threshold, the hydrated cement shrinks and the aggregates grow. Right. So you weaken the interface connectors between the cement paste and the aggregates, and then you are putting them into ball mill where basically they all rub together. Right. And you crush off the cement paste and are left with the pure cement paste.
Right.
and that again can be turned into a reactive material
Yes.
to produce the next
Yeah.
batch of concrete. So I guess in that level of circularity is something that might be impacted by using more and more fibers, but that would be probably a special case anyways, depending on the.
I was asking before, but so if it's possible to run the kiln through electricity, can we get enough heat? Without going down the weeds of how we get the electricity.
Oh, very very happy to go down the weeds, but I think there's two things. First of all, the Clinker facility consists of two stages, distinct stages. The first is so-called pre-calciner, which operates at a lower temperature, where most of the emissions occur.
So it's lower temperature. Is it going for longer? Or is that where we get higher
emissions?
emissions?
It's a bit longer. It's various stages where like the material is exposed to these high temperatures, and it releases the CO2 that's bound in the limestone. And that stage is there are technologies that would allow us to electrify that stage quite easily. It's a bit more tricky with the actual kind of the rotary kiln, where the material enters this long drum that is turning. And at the end, you typically have a very hot fire that blasts into that long pipe.
Yeah.
And technically, there are a few people thinking about plasma technology, for example, which is electric. You can fire plasma torch with electricity. Plasma torches have a relatively short lifetime and require a lot of maintenance. So it's something that might come further down the road. It's a similar thing that the steel industry is exploring. So there might be kind of scaling effects from doing it in a couple of industries. But that requires obviously much greater rebuild of the furnace, of the whole structure. Especially like the pre-calciner thing, that's essentially a new facility, an electrified facility, versus where we today basically use the off heat of the rotary kiln to supply the pre-calciner with the heat.
Okay.
So it's all, but I mean, the advantages.
It's not a silver bullet. Like assuming you had green energy.
Yes.
It still doesn't solve all your problems.
Yes. And you had basically, if you had no legacy and you were just building a new kind of brand new cement facility, obviously you might think about those kinds of technologies, because that would be.
Is it getting done overseas?
There are pilots.
Yeah.
It's probably not the scale that.
It's fascinating to see nuclear powered cement plants and the net carbon on that.
It's a very similar debate across all these heavy industries, and the steel industry too. And I think that's I guess you can be hopeful for the next couple of decades.
But Tim, this is amazing. There's so much that we're covering here, and there's so much more we can talk about. I'm gonna pause us there and split this into two. Because I think there's a lot of content here that's really, really valuable for the industry. But thank you for what you've given so far. And and then we'll pause and we will pick this up in the next episode. But thank you for episode 1. Thanks for the first part.
Thanks for having me, and
we'll catch you on the next one.
To the continued conversation, yeah.
Excellent, yeah. So thanks again for joining us for part 1, and stay tuned for part 2.